Hello, and welcome to today's lesson on the solubility of organic compounds, with a special focus on alcohols and their interaction with water. In today's lesson, we will recognize that most organic compounds are insoluble in water. Then we will understand why smaller alcohols can mix with water, while larger alcohols are less soluble. So far, we've explored the properties of different alcohols, specifically methanol, ethanol, propanol, and butanol. You are familiar with their physical and chemical characteristics, which will be fundamental to our discussion today. Building on this understanding, today's lesson will deepen our knowledge by examining how organic compounds, and especially alcohols, interact with water. This exploration will advance our chemical understanding by revealing the important role that molecular structure plays in solubility. Most organic compounds, like alkanes and alkenes, are insoluble in water and do not mix well with it. Instead, they often form two distinct layers, one layer of the organic compound and one layer of water. In most cases, the organic compound layer floats on top of the water because it's less dense. Alcohols, however, behave differently. They can mix with water more readily, but this ability depends on the size of the alcohol molecule. The OH group in alcohols is able to interact with water. This attraction between the alcohol's OH group and water molecules allows them to mix. This attraction isn't a chemical reaction, but rather a strong interaction that helps the alcohol dissolve in water. Let's look at the smaller alcohols: methanol, ethanol, and propanol. These alcohols have relatively short carbon chains and a single OH group. Because of this, their OH groups can interact effectively with water molecules, allowing them to mix completely. Because of this, we say these alcohols are completely miscible with water. They can dissolve to form homogeneous solutions, meaning that alcohol molecules are uniformly distributed throughout the water solvent. The solution formed has a neutral pH of 7, as the alcohols do not significantly alter the pH of the water. However, as the carbon chain of the alcohol molecule becomes longer, its solubility in water decreases. Let's take butanol, for example. The carbon chain part of butanol is hydrophobic, meaning it repels water and doesn't mix well with it. Although the OH group of butanol can still attract water molecules to some extent, the larger hydrophobic carbon chain interferes with this interaction. As a result, alcohols with longer carbon chains, like butanol, are only partially soluble in water, and if enough of them are added, they would form two layers. In summary, most organic compounds do not dissolve in water, forming separate layers instead. Alcohols, particularly the smaller ones like methanol, ethanol, and propanol, can dissolve in water due to the interaction between their OH groups and water molecules. However, as the carbon chain length increases, this solubility decreases. Understanding the solubility behavior of organic compounds can provide us with vital insights into many practical applications, including biochemical processes and industrial practices. In today's lesson, we examined the solubility behavior of organic compounds, with a focus on alcohols. We learned that most organic compounds are insoluble in water and form two layers when added to it. We then recognized how smaller alcohols are highly soluble in water due to interactions between the OH group and the water molecules. This property makes them completely miscible, forming a uniform solution with a neutral pH. We then discussed how the solubility of alcohols decreases as the carbon chain length increases and attributed this decrease to the longer hydrophobic carbon chain, which disrupts the interaction between the OH group and water, making these alcohols only partially soluble. By understanding the solubility behavior of alcohols, we gain valuable insights into various practical applications, from biochemical processes like how alcohols mix in biological systems to industrial practices where solubility plays a crucial role in product formulation and chemical reactions. Watch the rest of the GCSE chemistry course at Sophos Education.